I want to walk through an example using Raoult's law. So in this problem, we're going to focus on a non-volatile solute, so glycerin. So it's a covalent molecule, has tons of hydrogen bonds, it's polar. It has a density of 1.26 grams per milliliter, and we're going to take 50 milliliters of it at 25 degrees Celsius, and we're going to add it to 500 milliliters of water and mix it up. So we know the vapor pressure of pure water is 23.8 millimeters of mercury at this temperature. But what will be the vapor pressure of the solution? So we expect it to go down because we're adding a solute. And we'll use that equation that we just presented, that the pressure or the vapor pressure of the solution will equal the mole fraction of the solvent times the vapor pressure of the solvent. So we know that vapor pressure of the solvent already, right? That's going to be our 23.8 millimeters of mercury. So now what we need to do is solve for that vapor pressure, or sorry, that mole fraction of our solvent. So let's go ahead and do that. So for this one, we're going to start with what I'm going to do is figure out the moles I have of glycerin, and I'm going to figure out the moles I have of water. And from there, I can actually calculate my mole fraction. So I'll start with the glycerin. I've got 50.0 milliliters, and I know its density. So I'm going to multiply that by the 1.26 grams per milliliter. And then I'll multiply this by the inverse of its molar mass. So I can actually get this into moles instead of grams, which I don't really want. So 1 mole over, and I just calculated this off the periodic table for glycerin, which has a chemical formula of C3H8O3. So this will be about 92.09382 grams per mole. And when I plug that in, I get 0.684 moles of my glycerin. All right, now I got to do this for water. So I've got 500 milliliters. So I'm going to follow the same procedure. I'm going to use the density, which I forgot to include in the original problem, but at 25 degrees Celsius, the density of water is 0.997 grams per milliliter. So I'm going to multiply that by that 0.997 grams per milliliter. So now I have the mass of my water. And then I'm going to use the inverse of its molar mass to get the moles. So I'll multiply that by 1 mole divided by 18.015 grams. And that's going to give me a larger number of moles, right? As expected, 27.67 moles of water. All right, so now I can calculate that mole fraction. So what I'm going to do for my mole fraction, and this depends on if you're doing it for the solute or the solvent, right? And I want it for the solvent. So that means it's going to be on my numerators, the number of moles of my solvent. So this is for the water. So I'm going to take those moles of water and put that on the top of my equation. Now I'm going to divide by the total number of moles in my solution, which means adding together the glycerin moles and the water moles. So it'll be that 27.67 moles plus my 0.684 moles. So my total number of moles of my solution is not that different than the moles of my solvent, right? So I actually get a value that is not surprisingly 0.97589. Keeping all my digits. I'll round at the end. And that doesn't have units, right? Because my units cancel. Okay. I expect the vapor pressure of my solution to be very close to the vapor pressure of water as a pure substance at this temperature. But let's figure out exactly what it is. So to calculate this, I'm going to take that mole fraction I just calculated and plug it into my equation. So my 0.97589. And now I'm multiplying that by the the vapor pressure of my solvent, just the water on its own, the 23.8 millimeters of mercury. And when I calculate that, I get 23.2 millimeters of mercury. And so that's how different my vapor pressure will be for my solution versus my solvent at this concentration.